Alright, so this is Unit 6 homework packet, pages 1 and 2, and we are going to begin with empirical versus molecular formulas. So first we want to kind of define what these things are. An empirical formula is the most simplified version. It gives you only the ratio of the elements that are in your compound. So what this means is you should not be able to simplify an empirical formula at all. You should not be able to divide it by any common divisor. So this one, for example, C2H6, these are both divisible by 2. You can divide 2 by 2 to get 1. You can divide 6 by 2 and get 3. That means this is a molecular formula, not an empirical formula. Because an empirical formula is going to be as simplified as you can get without making a fraction. So the one right below it, this calcium chloride, that is an empirical formula. I cannot simplify that any further without creating a fraction. So that is what I'm looking for. So I'm going to look at the next one. This one I cannot reduce any further as well. So this is an empirical formula. This one is not, because 2 is divisible by 2. So that is a molecular formula. Molecular, molecular, because you can divide these by 2. Molecular, even if you can divide it by itself, 6 divided by 6 is 1, that can be simplified. These cannot be simplified without creating a fraction. So this one's empirical. Same thing with this one. You cannot divide these further without making a fraction. This one you can. You can divide those by 2. So you want to be thinking about your even and odd numbers. Usually that's really a good indicator, because numbers like 3 and 5 together, or 2 and 3 together, you can't divide those without making a fraction. So that's kind of what we're looking for as your key. So if we want to write out the formulas ourselves, all you have to do is reduce it down as much as you can. So for this one, for example, this x6, y18, I just want to think, what can I divide these down to make it the smallest number possible? So 6 and 18 you can divide by 6, right? So I'm going to use 6 as my divisor. 6 divided by 6 is 1. We don't typically write out the subscript of 1 in chemistry. If you do, it's not technically wrong, but also you're not going to see that on a test, right? We never really write out the ones that are understood. So I'm going to say 6 divided by 6 is 1. I'm going to leave that x there. 18 divided by 6 is 3. So there's my formula. And let's do this next one as practice as well. Okay, so what can I divide these by? I want to divide them out maximally to get our ratio, purely the ratio. 30 is divisible by 5, so I'm going to use 5 as my divider. 5 divided by 5 is 1. I don't write out the ones usually in chemistry. 30 divided by 5 is 6. So, keep on going. Let's try this one out. Again, I just want to think, what can I divide these both by? In this one, 22 and 6 are both divisible by 2. That's the only way I can divide these out. So 6 divided by 2 is 3. 22 divided by 2 is 11. And I can't divide any further. Again, looking for those odd numbers. Those usually are a good indication that you've come as far as you can go. We cannot divide those any further without creating a fraction. Okay, so now I'm going to do 4 and 5 so you can kind of see the difference when we're going from empirical versus when we're going from trying to get to molecular. So in this one, we're just doing exactly what we were doing before. We want to take this, find their common integer, right? What can we divide them by that is in common? 5 and 15 can both be divided by 5, so that's what I'm going to do. I'm going to say 5 divided by 5 is 1. We don't write out our 1s in chemistry. And 15 divided by 5 is 3. So that would bring you to choice C. So number 5 is a little bit different. So instead of trying to get the empirical formula, on this one we're asking you to try and find the molecular formula. So you have to work a little bit backwards. You have to think backwards and think, what could I multiply these by? I want to multiply them by the exact same thing, just like what you were doing before, but we're going the other way. So I want to look at my answer choices and make sure that they've been multiplied by the same number. Okay, so here we have an understood 1, so it would be like this, C1H3. And I want to think, what can I multiply them by that is the same thing? Okay, so let's just first try multiplying each of these subscripts by 2, because that's a good place to go, right? Next number. So 1 times 2 is 2. If I multiplied that by 2, and 3 times 2 is 6. Already I see an answer choice that has that there. So this is the correct answer, and let's think about why maybe choice C would not be correct. Okay, on this one, we've multiplied the carbon by 3, okay, because 1 times 3 is 3, but that is not what we did with our hydrogen. You can't even get to 8 with the 3 without using a fraction. So that is not a good answer choice, because it's just not a possible answer, because in the first, you have to multiply them by the same number. Okay, so look at the answer choices first on this one, and start with the 2's. If you can't find a common denominator with 2's, go up from there. But a lot of times it's just with the 2's, and then you can increase from there. It's just working backwards. That's all we did. All right, so next part, we're going to practice our scientific notation and standard notation. Before we do that, empirical versus molecular, I'm going to give you your first extra credit opportunity. You can write in +3, Empire Strikes Back. I'm a big Star Wars fan, and this is what empirical formulas bring to mind. So there you go, +3, Empire Strikes Back. All right, so we're going to do our standard notation. I'm starting off with a scientific notation. If you see that the exponent is a positive number, right? It is not a negative number. That means it's a really large number. And that means you're going to have something that is much bigger than 1. Or maybe a little bit bigger, but it's definitely not going to have a decimal point in the front. It's going to have zeros in the back. How many zeros? 7. So I just need to write a 7 and then just count. 1, 2, 3, 4, 5, 6, 7. That's the answer. Easy as that. Same thing with this one, except now I have 6 zeros. I'm going to write out my 2 and then just draw in 6 zeros. 1, 2, 3, 4, 5, 6. What if you're going the other direction? Same idea, except instead of being a really large number like these numbers, these are really small. How small? We're going to go back. I'm going to start with it just the way it's written, 6.1. Now I have to think I need to move this decimal place 11 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then fill in all those zeros. So it is 6.1 with 10 zeros in the front. Okay, so just got to move that to make a very small number. I'm going to move again. On this one it's -5, so I'm going to write out my number and then move it 1, 2, 3, 4, 5 places. And then you can go the other way quite easily as well. This is a really large number, so it's going to have a positive exponent. What is my positive exponent going to be? Let's count. 1, 2, 3, 4, 5, 6, 7. So it's 6.0 times 10 to the 7th. All you have to do is just count, plop down a decimal point if it's a really large number, and then move over until there's only one digit in the front. And that's how how large your exponent needs to be. So on this one, I plot my decimal down at the back of the number, and then I'm going to move it 1, 2, 3, 4 times, because I only want one digit in the front. Now, if you're dealing with a small number, it's the same concept. You only want one digit in the front, so I want to get it to say 5.7, and I just have to think about how many times I moved that in order to make that happen. 1, 2, 3, 4, 5, 6, 7 times. But because it's a small number, I moved it backwards. That's where the negative sign came from. But I moved it backwards 7 times. So that is our scientific notation versus standard notation. You get a +1 for moving digits. Okay. So now let's go to page number 2. This is all some review information. Okay, so we want to think about Mendeleev versus Moseley. This is going from way back when. Who did what? So sometimes it's easier to work backwards from what you know. So Moseley created the modern periodic table. The modern one means it's what we use right now. So if you totally forget, if you just get out a periodic table and look at it, like any periodic table, you're going to notice that they are arranged in order, okay, by their atomic number. 1, 2, 3, 4, 5, 6, right? They are not arranged by weight anymore. If you look, some of them are out of order. So if you just use the modern periodic table, they're in order by their atomic number. That's our modern one, the one we use now. Look at the one you have now in front of you, and then you can use that reasoning from there. Moseley created the modern periodic table by rearranging the elements in order of their atomic number. Mendeleev, therefore, did it by mass. He did it by mass because that's the only way they really had to go by back then. They didn't know about all the stuff in the inside of the atom. So he did what he could. That was by mass. That is not how it is arranged anymore, and you can tell that just by looking at the periodic table. You can see that it doesn't follow that order. I'm trying to find one of my good examples here where it gets out of order. Well, trust me on this one. It's there. I'll find an example in a minute. Maybe I'll write that down as a bonus. But so Mendeleev did the first one by mass. Moseley created the modern one, the one we follow today, by atomic number / protons, right? Because that's the same thing. Okay, so quick review of all the periodic table things. I'm going to do this really fast. Halogens. Halogens are in group 17. That's the one students tend to forget. I'm not sure why, but that is in group 17 or 7A. And I remember this because, like, if you get really stuck, count the letters in halogen. 1, 2, 3, 4, 5, 6, 7. Halogen has 7 letters. Okay, alkaline earth metals. This has an extra word. So that's how I remember that it's number 2. Versus alkali metals, that's only the one word, or, you know, alkali metals, it's actually 2 words. But noble gases, way over there, are royalty, that's 18A. Why are alkali metals most reactive? They are the most eager to get rid of their one extra electron. That one extra electron is making them really antsy because they're really close to dropping down to their valence shell below. And that's the exact same reason why halogens are the most reactive. Non-metals, the same but opposite. They are very close to 18, very close to 8, right? Because you can't have 18. Very close to 8, very close to a full octet of 8. So if they can just get that one more electron, pick up one more electron, they'll have a full octet of 8. Really want one more electron to complete octet. All right, noble gases are the least reactive because they already have a full octet. They already have a full octet of 8. They don't want to lose anything. They don't want to gain. All right, so next things we are going to do is classify the following properties as physical properties or chemical. I'm not going to do all of them. I'm going to talk about a couple. Density tends to be one that students want to get confused with the intensive versus extensive. This is a physical property, right? So I'm going to label that as PP. The intensive versus extensive, this is actually something that students sometimes think is extensive because a lot of the other ones are kind of measurement type of things. But I like to remind students to think about throwing pennies into a fountain. It doesn't matter if I throw in my entire roll of pennies or just one penny, they're all going to sink, right? That's an intensive. It's independent of my amount. Okay? So it does not matter if you have extras. Unlike something like volume, which is also a physical property, but it is extensive. So I'm going to circle this because it says circle the ones that are intensive. Volume is extensive because extras do matter. Okay, if I have more of whatever, more drink, more Kool-Aid, whatever, the volume, the extra amounts matter. Okay, so you cannot have chemical properties. You don't describe chemical properties as intensive or extensive. That's only something we use for physical properties. So here, how about flammability? That's another one we can do. Flammability, that's a chemical property. If you burn it, it's not ever going to be the same. If something catches on fire, it's burning up, it will never be the same again. You cannot go back. The chemical makeup will not be the same. So that is a chemical property. We don't describe anything as intensive or extensive if it is chemical. It's just chemical. And here's another one that students usually mix up are boiling and melting points. They want to say that it is chemical, but if you change the states, right? If I boil water, I can get it back. I can take it back down and it can become liquid water again. So that's okay. That's actually just a physical property, and that is an intensive physical property because it is independent of the amount. Extras do not matter. Okay, so much the same properties. Physical changes and chemical changes are pretty much same idea when we're talking about the changes. The most missed ones I see students making are usually they'll try and tell me that dissolving is a chemical change when it's just a physical. You can get it back. If I dissolve something, I can boil off that water again and it'll be there. Okay, so this is just a physical change. The other big physical change that students mix up are, again, those state changes. So when I'm talking about something evaporating, melting, sublimating, these are just changing the states. You can go back to where you began with. It is just a physical change. So anytime you're going from solid, liquid to gas, these are all just physical changes. Unlike something like the word combustion, if something explodes, it combusts, it blows up, you're never going to get it back. Okay, that firework, you're never going to get a firework again. That little pile of ash is completely chemically different than what made up the firework. So that is a chemical change. Something like diluting is another one that students will try and say it's chemical, but it's not. You're just adding water. You can make it more concentrated again. So this is just physical change. But maybe if we see something like a brand new gas, if we're mixing something and they were just liquids before, there was no gas, like if you think about classic baking soda and vinegar experiment, right? We've seen that before. You put the baking soda and vinegar together, maybe in elementary school, to make a volcano. When you put those two together, you get a brand new gas, you get those bubbles. That is actually a chemical change. Okay, so little quick review of nuclear chemistry. Which type of radiation is the most harmful to our cells? We all know what happened to the Hulk. He was exposed to gamma radiation, right? The most harmful are those gamma. Okay, so then we're going to do fission, fusion, or both. Splitting, think about fission, division, okay? Splitting, fission, division. So that's fission. Nuclear power plants, that is when we see those fission happening, okay? A nuclear power plant is a fission reaction. Nuclear power plants, nuclear bombs, those are fission. Fusion, however, is what we see on the sun. Fusion doesn't release gamma radiation, but it does release a large amount of energy, just like we see on our sun and pretty much everywhere in the universe when stars form. That is fusion, coming together. So that happens when some nuclei that are very light and unstable combine together. That is fusion. Think about fusing together wires, right? So combining, that's going to be our fusion. Splitting, that's going to be your fission division. Large amount of energy, guess what? That's both. Changes the nucleus, that is also both. Okay, in fission they divide, and fusion they combine. So that is our first video, and what the heck? We'll just go ahead and add another +2. You can write fission, division, and give that a circle. All right, we'll see you in the next video.